Hello friends. Today we're going to solve a polynomial inequality. And so whenever we're dealing with inequalities, that means we're dealing with greater than, less than, greater than equal to, less than equal to, not equal to. Those are all inequality symbols. So they're used in the place of an equal symbol, but they don't mean equals. They mean something similar but slightly different. And the main thing we need to remember is we are going to write our answers using interval notation. So in order to do these problems, and I like to write my steps out like a recipe, we're going to replace the inequality or treat it as though it's an equal sign. And we're going to rearrange that polynomial so that it is equal to 0. And it's important to the interpretation that you have equal 0, that 0 is on the right. So the equation is isolated on the left and you have it in relation to 0 on the right. So once we do that, we'll be able to solve that equation and find the zeros. And these are going to be what we call critical numbers. After we have these critical numbers, these values, we're going to plot them on a number line. Doing this will break the number line into intervals, and then we can choose test values. Okay? So we're going to choose test values, and we will check each test value back in the original inequality to determine whether or not it gives us a true or a false statement. All right, so once we're done with that, we will be able to write our answer in interval notation. And we just want to make sure we pay attention to the difference between a bracket or a parenthesis. So a bracket means you can touch that point, and a parenthesis means you can't. Okay, so a not equal to situation. All right, so here we have a quadratic polynomial inequality. And what we're going to do is I'm going to rearrange this, isolating my terms. So I could subtract 5x from both sides, and that gives me minus x, as well as subtract 9 from both sides, which gives me negative 2. So I have it in relation to 0. We want to make sure that we treat it like an equal sign because we're going to solve this equal to 0. So even though that greater than or equal to 0 is what we're going to ultimately be considering, for our solving purposes, we turn it to an equal sign. Most of the time, the quadratic equation you get here, or the polynomial you get here, should be easily factorable. And in this situation, I can say I got x minus 2 and x plus 1 is equal to 0. So very easily, I can see that the zeros of this, which I'm going to call critical numbers, those zeros are going to be x is positive 2 and negative 1. So from our steps up above, we're going to take that positive 2 and negative 1 and plot them on a number line. So at this point, we're going to choose a test value. So I've plotted 2 points on my number line, and that has created 3 regions, 3 intervals. I have negative infinity to negative 1, negative 1 to 2, and 2 to positive infinity. So you can see this has been broken into 3 separate intervals. And we are just going to test a test value, any number on that interval. I'm going to pick x equals negative 2, x equals 0, and x equals 3 as my test values. And I want to test them in this original inequality statement to see if I get true or false. If it is true, that means I'm going to include that interval in my solution set. And if it's false, I'm going to have to leave that out. So I'm going to come down here. I'm going to test x equals -2, which gives me -2 squared minus -2 minus 2 is greater than or equal to 0. So that is 4 plus 4 minus 2 is greater than or equal to 0. And we get that that is a true statement. So this region, because we got a positive output here, and that is a value that is greater than or equal to 0, we include that. So I'll test again. I'll test x equals 0, which gives me 0 squared minus 0 minus 2 is greater than or equal to 0. And here I get -2 greater than or equal to 0. And that is not true. That's a negative value. So we will not include that in our solution set. And so we have one last test value that I'm going to plug into that. I'm going to test x equals 3. So testing x equals 3, I have 3 squared minus 3 minus 2 greater than or equal to 0. So 9 take away 3 is 6, take away 2 more is 4. We end up with 4 greater than or equal to 0, which is true. Okay, so we get a true statement here because we ended up with a positive value when we plugged that in, and a positive value is greater than or equal to 0. So when we want to write our solution set, we know that everywhere to the left of -1 and to the right of +2 is going to be included. So the only thing we have to think about is, am I going to use a bracket or a parenthesis at each of those endpoints of those intervals? And because the inequality given says equal to, and these critical numbers that we found are basically zeros. A 0 is a point on the x-axis, and the graph is equal to 0 there. So my solution set, my final answer here, I'm going to have a bracket shading to the left of -1 and a bracket on 2 shading to the right of 2. And when I write my answer in interval notation, I'm going to say -∞ to -1 union, and as I just said, that needs to be a bracket, union 2 to +∞. And this is my solution set. All right, so there's a little bit more to this we can think about. And if you have your calculator, that would help you as well. But if we look at graphing this function, x squared minus x plus 2. So what that looks like, that's a parabola opening up, and it crosses the x-axis at -1 and also +2. So in this regard, if we say, where is the graph greater than or equal to 0, greater than or equal to 0 is above or touching that x-axis. And so considering where this graph is above or touching the x-axis, everywhere to the left of -1 we are above, and everywhere to the right of +2 the graph is above. So you can see that -∞ to -1 union 2 to +∞ occurring when you look at the graph. So let's do one more example here. We're going to solve 2x cubed plus x squared less than 10 plus 11x. So again, this is the same as 2x cubed plus x squared minus 11x minus 10 needs to be less than or equal to 0. And when I think about that less than or equal to 0, what that lets me know is I need to be below the x-axis, and not equal to means not touching. Okay? So we need to factor this. We're going to treat this like an equation equal to 0 and factor it. We don't know how to factor this. Well, we can use our rational zeros theorem, which we talked about in the previous section. And the rational zeros theorem says the possible rational zeros are going to come from plus or minus factors of the constant. In this case, the constant is 10. So 10, 5, 2, and 1, those are all factors of 10, divided by factors of the leading coefficient. And the leading coefficient here is 2. So I have a list of 6 possible rational zeros. That would be plus or minus. I have 5, 10, 5 halves. There gets another 5. 2 over 2 is 1. 2 over 1 is 2. 1 over 2, we've got 1/2. Okay, so I've got those 6 numbers when I match up each term in my numerator with each term in my denominator. We had a little overlap, so some reduced. And then we do plus or minus, which gives us doubling that set of 6, 12 possible zeros. And we're just going to pick one of them to test. And because I want to speed this up, we're going to use -2. So I'm going to test x equals -2. Testing x equals -2 with my synthetic division, I'm going to list my coefficients, 2, 1, -11, and -10. The 2 comes down. -2 times -2 is -4. You add down. -3. +6, add down. -5, multiply up. +10, we get a remainder of 0. Okay, so that's what we wanted. And what we learned in previous section is that now I've factored this. I'm dealing with x plus 2, because remember that is coming, that's the 0, so the factor theorem says we would say x minus -2, so we've got x plus 2, and because it was cubic, my quotient here, 2x squared minus 3x minus 5. And in order to find the zeros, we need to continue factoring this. We could repeat synthetic division, or we could notice that this factors and I get 2x minus 5, x plus 1. So we are trying to see where this is below or not touching the x-axis. Okay, if we treat it like an equation, my zeros, or my critical numbers, are x equals -2, +5 halves, and -1. So again, we make a number line and we can test things on the number line. But what I think is a little easier is to actually make a graph. So we have -2, -1, and 5 halves here. Those are those values. And those are points on the x-axis. So what is my graph shaped like? And if we go back and we think about our leading term test, this is an odd degreed function, which means we have opposite ends, and it's rising left to right since the leading coefficient is +2. Okay, so we know it has that end behavior shape. We're going to start low and end high. And then also thinking about multiplicity, each of these factors, where those values came from, each of those factors have a 1 as their multiplicity. That's the exponent on each factor. And k equals 1 is an odd multiplicity, which lets us know that we're going to be crossing at all of those zeros. So if I went to graph this, and I'm graphing it by hand because I want you guys to get practice, but you do have your graphing calculator, we are going to see that the function starts low. We're going to go up, cross at -2, down, cross at -1. We have to turn around again, and then we would cross at 5/2. So if we go back to the very top and we think, well, where is this less than 0? We are below the x-axis, to the left of -2, and also between -1 and 5/2. And are we allowed to touch at any of those values? And because the original inequality sign did not have an equal to, the answer is no, we cannot touch there. So my solution set for this problem is that x is some number from -infinity to -2, parenthesis, because we can't touch, union -1 to 5/2. And this is what you would be expected to write here in the box.